Hi, David.
Hi, Bob.
How you doing?
I'm good.
Good. Let me introduce us. I'm Robert Wright. This is The Wright Show. You are David Mark Wallace, professor of philosophy at the University of Southern California. Am I right so far?
That's right. Yep.
Well, good, because my record may get worse as we start to talk about quantum physics. I may event some misunderstanding. Anyway, I'm really looking forward to this because I love talking about weird aspects of quantum physics. We're going to talk about arguably the weirdest aspect, the so-called many worlds interpretation of quantum physics. People have heard of it, already know how weird it is, and the rest will shortly understand, or at least get some sense of how weird it is. Now, it's an idea that has been taken more and more seriously, I think, in recent years.
Yeah.
By physicists and by philosophers of physics, and it is said that no one is more responsible for this fact than you. You've written a lot of papers. You wrote a book called The Emergent Universe, Quantum Theory. Yeah. What did I say? Universe?
It's multiverse. Yeah.
Right. The Emergent Multiverse, Quantum Theory according to the Everett interpretation. Everett refers to Hugh Everett, who first posited what's now sometimes called the many worlds interpretation. And you also co-edited a book with Oxford called Many Worlds, Everett, Quantum Theory and Reality.
Yes.
So I guess one way to start trying to explain this idea of many worlds, and then we'll get to the weird part shortly, but to set it up, why don't I try to tell you the kind of a problem or puzzle that I think it is intended to solve, and you can stop me once I start getting things wrong, which shouldn't take long.
Sure.
So I gather that the math of quantum physics is sometimes predictive only in a probabilistic sense, right? So in other words, you're about to measure some electron, and the math can predict, it can't predict exactly where you will find the electron, but it can say, well, there's a 50% chance it'll be here, 25% chance it'll be here, 25% chance it'll be here. And if you repeat that enough times, you'll see that the math did accurately get the probabilities right, even though it can't tell you for sure in any one case where the particle is going to be. So the question is, what do we make of that? The most commonsensical approach is to say, well, is so-called hidden variable approach, which was Einstein's preferred interpretation, is that, well, there's just something we don't understand. There's some variable we're failing to measure. If we could measure it, it's somewhere there in the physical system. If we could pick up on it and plug that into the equation, we would be able to predict exactly where the particle is. That's now discarded by physicists with confidence, I gather, right? The hidden variable?
Yeah. Well, kind of. I mean, let me qualify a little bit. So, the math in itself doesn't tell you anything directly. There's always some sense in how we interpret the math. What the math does is it says something. It assigns a thing called a quantum state to the thing being measured, and the quantum state is something like, this isn't literally how the math works, but it's something like 0.5 particle here plus 0.25 particle here and 0.25 particle in the other place. And then the way we use the theory to make predictions is we interpret those numbers as probabilities.
Right.
And one worry you might have there, which leads to the sort of hidden variable line you're talking about, is you might just say, well, I'm philosophically uncomfortable with a theory that only traffics in probabilities. I want the theory to tell me more about what's really going on and give some kind of underpinning to those probabilities, so that the probabilities are just a sort of gloss on the underlying story. And the sort of hidden variable story you're talking about has that kind of character. But, if that was the only problem, I don't think we'd be too stressed, because it doesn't seem crazy to think that maybe the world just has probabilities written into it at a deep level. Maybe it really is the case that the laws of physics are themselves sort of probabilistic things. That the puzzle's worse than that. The puzzle is that while we can sometimes interpret the math of quantum mechanics in probabilistic ways, there are other circumstances, more those to do with microscopic physics, where interpreting the math probabilistically just gets into a straight contradiction.
Even though the math has that same structure you just described, which is the equation itself would say 0.5 particle, 0.25 particle, but for reasons we probably shouldn't get into, probabilistic interpretation just wouldn't make any sense.
That's right. I mean, I can get in the reason a little bit without getting technical. Part of the reason is that the probabilities in ordinary probability theories can just add up. If I've got probability 0.25 of this thing happening one way and probability 0.25 of this thing happening the other way, I just add those numbers up and I get probability 0.5 of it happening one way or the other.
Right.
The numbers in quantum mechanics, when you add them up in the same way, they can sometimes cancel out. So without getting into the details of how this works, you can have a circumstance where the math says it's got a probability 0.5 of happening, that A happens this way, and a probability of 0.5 that A happens that way, but probability 0 that it happens either way.
Okay, I'm definitely not going
to... That can't make sense.
No, I'm definitely not going to ask you to try to get me to make that seem to make sense, because I don't think I want to be the kind of person that would make sense.
Well, it shouldn't make sense.
Right.
What that tells you is those numbers can't have been probabilities in the first place.
Right.
You remember what I was saying? The math itself can't tell us what happened.
So
the math looked like they were probabilities, but they can't be. At least
so
not
this is one of the reasons that the hidden variables interpretation is frowned on. Because of this wrinkle.
Yeah, pretty much. Yeah. So you have these scenarios where, I mean, one of the standard experiments is something like the ray of light goes along the left path or the right path, and then you see where it goes after that. So you can see what the probability is that it goes along the left path and does this or that, and you can see what the probability is that it goes along the right path and does this or that. So if there's a hidden variable theory, then one of those things is true. Either it went along the left path or it went along the right path.
Oh, right.
And we can sort of reason on that basis. And we get situations where if it definitely went along the left path, then the two places it could end up are equally likely. And if it definitely went along the right path, the two places it could end up are equally likely. What we actually find is if we let it go along either path and we don't look where it goes, that doesn't turn out to be right. It turns out that you can arrange things so the light always goes in one direction. And if there was a hidden variable theory, couldn't make sense of that, or at least not a hidden variable theory of the kind you're talking about.
Okay, so this sounds a little reminiscent in structure to the famous, the machine gun shooting the things through the two slits and so on, which we probably shouldn't get into. But it's that kind of thing where whatever's going on in between the two times you look at it are what make things weird, or what confound a strictly probabilistic, a straightforward story.
That's basically right. I mean, what you basically have is a piece of math that it gets often talked about as when we don't look and when we do look, but what's really going on is, are we talking about microscopic stuff or macroscopic stuff? And this is a piece of math that, if we try to understand it probabilistically at the microscopic level, just doesn't work. It gets contradictions and doesn't make sense. But it's also a piece of math that we seem to have to understand probabilistically at the macroscopic level in order to get out the predictions that quantum mechanics uses, the probabilities you were talking about earlier.
Okay. So there's hidden variables. One way that people have tried to wrestle with this and don't much anymore. Now, then we come to another thing that is still not the many worlds interpretation, but is much more commonly heard. Mm-hmm. And as I understand it, the idea is that if you ask, okay, so we have this probability curve describing where the electron will be when we measure it. And if you ask, well, where is the electron right now, like right before I measure it, the answer is something like, is nowhere in particular. Maybe some people might want to think of it as being actually a single electron being in more places than one at once. Some people might think of it as being in none of those places. But in any event, the idea is that it has no definite existence of the kind it will have when we measure it. And the act of measurement, in some sense, forces the so-called wave function, the probability wave, to collapse onto a single point. And so the act of measurement brings it into definite existence in some sense. Now this in turn bifurcates or more into different there have been people, I don't think this is common, there have been people who got weird and said, well, maybe it's the consciousness of the observer of the measurement who's bringing it into definite existence, which would be consistent with the whole tradition of Eastern philosophy in particular about the relationship between consciousness and matter. But I think the much more conventional idea is that it's just the physical measure, it's just collision with a physical measuring device that brings it into definite existence, right?
Yeah. But the problem with that idea is even though in some sense it's less mystical than the idea that my consciousness has a special role in physics, it still says that my measurement device has a special role in physics. And the problem is my measurement device is just more particles.
Right.
So what we seem to be doing is applying a very different physics to a bunch of electrons and atoms when they're part of a measurement device than we apply to them when they're just ordinarily getting on.
It's like, how would an electron know that running into a little piece of lab equipment is any different than running into a piece of anything else? Why would it behave differently?
Exactly, yeah.
So that leads us, having discarded all alternatives, we are converging on the Hugh Everett interpretation, so-called many worlds, and maybe I should at this point let you tell me when you're addressing lay people, how you describe to them what many worlds says.
Yeah, sure. So I think it starts with that idea of the electron somehow being in two places at once. So the basic formalism, the math of the theory, seems to say electrons and atoms have to be in two places at once. A whole bunch of experiments look impossible to understand unless they let electrons be in two places at once. And the problem that often gets called the quantum measurement problem is that somehow at some point things need to stop being in two places at once, because it looks like we just never see them being in two places at once. And so either you end up with consciousness doing that, or special roles for measurement devices, or some other ideas, we don't know. So what Everett really asked, in effect, was, well, hang on, how do we know that things have to stop being in two places at once when they get larger? So the argument, sort of in lay terms, goes something like this. I mean, suppose we do something like the famous Schrödinger cat experiment. So we arrange something where the electron is here and there at the same time. If it's here, we kill the poor cat. If it's there, we leave the cat alive. So the theory predicts the cat's alive and dead at the same time.
Right. In this scenario, there's like a box. The cat's inside, and if you ask the question, "Is the cat alive or dead?" there's a certain piece of logic that leads you to believe it's both or neither, and there's no definite answer because the cat's fate depends on which way the particle,
That's exactly right, yeah. So then if I look at the cat, what the theory literally says is now, because my looking at it is just one more physical process, what the theory says is not David should see a weird superposed cat. It doesn't say that seeing a cat that's alive and dead at the same time would be like seeing double. It says that I should myself now be in two states at once. I should be in a state of seeing a live cat and a state of seeing a dead cat at the same time. Mm-hmm. And if you ask me, well, what was the cat like? Then again, just applying the physics says you should now be in two states at the same time. A state of hearing me saying it's alive and hearing me saying it's dead at the same time. And anyone who watches this podcast, they end up in a state of hearing us talk about a live cat and hearing us talk about a dead cat at the same time. And this is just what all the math says. And all these things stay correlated is the key thing. So it's like the system as a whole of you and me and the listeners and all the stuff around us, that system as a whole is now doing two things at the same time. One of those things is a things playing out as if the cat was alive thing. One of those things is a things playing out as if the cat was dead thing. Mm-hmm. So that there are the two things happening at the same time, but there's no observer who somehow gets to see double. We just have these two parallel processes playing out. And when you've got two parallel processes playing out on the scale of the whole planet, each of which internally to itself just looks like an ordinary definite set of goings on, it becomes pretty natural to use language like two worlds to describe those goings on. They're not worlds in some fundamental sense. We haven't split the universe as a new law of physics. It's just that the actual goings on in the universe, according to quantum theory, just are very naturally described in terms of multiple parallel goings on at the same time.
But an implication of that, if you apply it to the real world, is that there's more than one of me.
Absolutely, yeah. Quite a lot more than one.
And they are doing different things off in different worlds. I mean, just to quickly review, to get back to the electron example, the answer is, well, wait, I measured the electron and it's here, so wherever it was there, it must have collapsed on this. You would say, well, no, actually, there is a world in which the electron is being measured over there, and it's found to be over there, and there's a version of you that's doing that measuring, and you might as well wave goodbye to that person because it will now follow a separate track from you, even though you had a shared history up to this point.
That's right. On the traditional story, the electron used to be here and there, but now it's only here, and I see it here. On the many worlds story, the electron is still here and there, and I see it here and there. i.e. there's a
Well,
version
I,
of
so to
the,
speak, you might say
well, with
I superscript 1 and I superscript 2,
exactly,
two
that's
different
exactly
versions
right.
of I.
That's right. If you do a sort of third-party description, instead of it being electron's now here and David sees it here, it will be more electron is here and there. There's a David who sees it there here, and there's a David who sees it there.
Mm-hmm. So people probably now understand what I meant by weird.
Sure. Yeah.
How, how literally, I mean, you're kind of a believer, right? This is your preferred interpretation.
Yeah, and I get nervous about language like believer, but it seems to me the most plausible way of making sense of it. I think it's probably right in at least its broad details.
In fact, I mean, a fellow proponent, David Deutsch, I think has said it's wrong to use the term interpretation. The other things are interpretation. This is just what the theory said. That's how straightforwardly he sees this so-called interpretation as following from the theory. Does that make sense to you?
Yeah, I mean, I'd say something a little more nuanced. I mean, I think you get Everett from the theory if you make two choices. The first choice is don't change the equations, and the second choice is don't change your philosophy. So the normal philosophy we have for scientific theories is basically we just take the mathematical description fairly literally. We say when the equation describes multiple bits and pieces, then there really are multiple bits and pieces in the world doing what the equations say. You could imagine that we said instead something like, well, scientific theories are just gadgets to predict the result of experiments, or scientific theories should be understood as not describing a world independent of an observer or something. But if we hold on to the philosophical view that scientific theories are sort of objective, independent descriptions of the world, and we hold on to the equations of quantum mechanics themselves, then we basically get the Everett interpretation. So I almost agree with David. I guess what I'd say is that many worlds is the literal interpretation of quantum theory. There are various sorts of non-literal interpretations you might make, but if you don't want to do that, if you want to treat quantum theory just the way we treat any other scientific theory, and if you don't want to change the equations in the theory, which I think is wise because the theory is really, really successful, then you pretty much get the Everett interpretation.
Okay. So, if you take it seriously, I mean, I'm sure the first question people might ask is like, where is this other me? I mean, people are inclined to think of three-dimensional space. It seems pretty crowded. It's already occupied by this universe. So that's like one cognitive challenge we face, right? Is like, where is the other me, right? And what's the answer to that?
Okay, so it's kind of subtle. Let me answer in a couple of steps. So part of the problem we have here is that to really talk about a quantum theory of where everything is, we need to understand the quantum mechanics of space and time, and we don't, as I'm sure you know, we don't yet have a full quantum mechanical theory that handles space and time. So if you say what's the answer according to the best quantum theory we have, in those theories, space and time are just a background; they're not quantum at all, and we're just our lives are playing out against that background. And if that were true, then these other worlds would be in the same space we're in. It's just that they wouldn't be interacting with us at all. And that might seem weird, but of course, we actually know in science anyway, independently of quantum mechanics, that whether two things interact is not whether there can be things in the same space as me that I see is not a matter of some metaphysical requirement that two objects can't be in the same place at the same time. It's just a matter of what the equations are that govern how they interact. So right this moment, millions of neutrinos are sleeting right through your body. Your body is full of high-speed neutrinos coming out of the sun. They don't interact with you at all. You can't see them. Why is that? Just because it's what the equations say. So, and what the equations say in the many worlds theory is that those various worlds are also in the same space you're in. It's just that precisely because of the equations, they're not interacting with you. Having said all of that assumes our current best quantum theories where space and time is a background, but we're sure that's false. If you look at the way
we're sure that what is false?
We're sure the idea of space and time just being a classical background is false. We're sure we know from Einstein's general relativity that space and time react to the presence of matter. So in a quantum theory, if a heavy weight could be here and there at the same time, then space should react this way and that way at the same time. And if that were the case, then there'd be many spaces. just as there are many worlds. So what we actually sort of expect in hand waving terms is that a quantum theory of gravity, a quantum theory of space and time, would actually say that when multiple worlds happen, space itself branches, and there are multiple different spaces where these worlds are playing out. But that's all quite qualitative. We don't have a consensus on how that works mathematically. String theory is the nearest we have, and I'm no expert on string theory, but string theory is not fully developed, isn't empirically supported yet. So these are kind of speculations as to how quantum theory would turn out when space and time are included in it.
But in any event, we know there's a deficiency in the way even physicists currently conceive of space and time in some sense, or an incompleteness about it. And it could be that when they come up with a better way of looking at it, a more quantum compatible, then it will kind of accommodate the many worlds interpretation in a natural way.
We've got strong reasons to think that. I mean, the thing to remember about quantum mechanics, it's not a single theory. It's a kind of framework for a lot of theories. So we started with a quantum theory of atoms and molecules, and we developed a quantum theory of light and a quantum theory of fields. And the standard model of particle physics that gets tested at CERN is a quantum theory, and string theory is a quantum theory. And any given quantum theory can be if you take it literally, is a many worlds theory. So if there is a quantum theory of gravity, and we take that theory literally, it will tell us that it's a many worlds theory, and those many worlds will be different ways space itself could be.
Okay. Now, you said there are many more than two of me, according to this view. Like, how many? I mean, it sounds like a naive question, but what I mean is, like, what I'm really asking is, like, what is it that causes things to bifurcate? When do they bifurcate? I mean, It isn't just when we measure them, because you've discarded the idea that measurement itself is fundamental, right?
Absolutely, yeah.
So what is it?
So the splitting happens, according to the equations, whenever some microscopic level indeterminacy, some micro level thing is here and there at the same time, gets magnified up to the macro level. In other words, when you've got some large scale phenomenon like you or me, that would go a different way if the electron was here than if the electron was there. So one way that can happen is if I build a measurement device and look. So another way it would happen is if just some natural phenomenon amplifies it up. So you've ever seen one of those broken fluorescent lights where it's flickering?
Yeah,
I
have one. I own one. Yeah.
So those flickerings are quantum mechanical. Whether it flickers one way or another is a quantum random process. So according to reading the quantum mechanics literally, according to many worlds theory, the fluorescent light flickers this way and that way at the same time. So every time you look at light, that causes you to split. When cosmic rays come through and cause or don't cause mutations, that causes splitting.
So well, is the question then, like, is it that whether or not the simultaneous coexistence of two versions of an electron leads to a splitting depends on whether it's part of a structure such that this kind of, has large-scale implications. I mean, it might or it might not. It might be that there's, like, two electrons next to each other. There's two versions of each of them, and somehow they neutralize each other so that the causal implications of that do not go beyond their realm. But it might be that there's a cascade. It might be there's, on the other hand, a cascade of interaction that means it's significant at the macroscopic level. And you're saying that is the question?
Yeah, that's exactly right. So what you tend to find in the maths of what's called decoherence theory which is what governs this splitting process, is that once you start getting above a certain scale, it gets irreversible. And the reason for that is because when a system is doing two things at once, its surroundings tend to notice, and the bigger it is, the harder it is for the interaction with the surroundings to be controlled and suppressed and cancel out, as you're saying. So at the micro level, it's often pretty easy. I mean, that's a lot of how quantum mechanics explains things. A bar of metal is a system where electrons are in lots and lots of places at the same time. That's how metals conduct. But that's a process where it's all kept confined and controlled. But if you try taking that bar of metal itself and putting the bar in two places at once, the environment it'll notice. The environment will behave one way if the bar's here, a different way if the bar's there, and then the environment will do that, and the whole process will cascade.
And is there a way of thinking about kind of the size of, the size beyond which things become uncontrollable, an actual, like, volume of space where if things are not neutralized internally, then we're going to see another world created?
There is, but it's to some extent a matter of how clever the experimental scientist is. So as a practical matter, unless you control a process pretty carefully, once you start getting up to the scale of, I don't know, big molecules or small cells or a virus or something like that, then it gets very difficult to prevent. But very clever experiments can manage it. People have done superposition experiments with viruses where they've been in multiple states and then stopped being. What really matters isn't so much how big the system is, it's how many different bits of it are trying to do two things at once. Mm-hmm. So even a relatively big object, if you're very careful and you isolate it, could have its center of mass here and here at the same time. But if all the different bits of the bar are trying to do different things at the same time, that gets really hard. I mean, you've heard about the project to make quantum computers.
I have, yeah. So I was gonna bring that up.
Yeah, I mean that project is exactly a task of trying to get the whole computer to be doing multiple. And this isn't the whole of what a quantum computer is about, but it's part of it. Trying to get it so that it can do multiple computations at the same time, without that getting irreversible, without the cascade happening.
I see. And as long as we're on this subject, I mean, part of that, in at least some cases, is, I gather, and this could turn out, I think, to be a kind of a corroboration of many worlds, is like, in some cases, the idea is to get a single electron, to get the different versions of an electron to simultaneously do different bits of computational work. That's where some of the power could arise from?
That's where some of the power is, yeah. I mean, that basic idea of parallelism, that I can have multiple quantum processes happening at the same time, and then somehow at the end of that process I can do something clever to get one answer out that's the same in all the worlds. That was the sort of core idea of some of the very first algorithms in quantum computation. And certainly David Deutsch, who was one of the founding fathers of quantum computation, had exactly that kind of intuition in mind when he was trying to work out how we might come up with a quantum algorithm. Now, it has to be said, to be truthful about it, that particular way of coming up with quantum algorithms hasn't been that fruitful beyond some of the earlier ones. And the thing to think is that massive parallelism is one particular trick you might try with a quantum computer, and there aren't many known ways of exploiting it effectively. And some of the other things we'd like to do with a quantum computer just don't naturally fall into that parallelism discussion.
Okay, so if massive parallelism works on a quantum computer, you would take that as evidence in favor of many worlds.
Yeah, well, I'd be a bit nuanced. I'd say it's evidence that quantum mechanics is right, and it's evidence that if there are any modifications of quantum mechanics that get rid of the parallelism, they have to happen at a scale bigger than the computer. But of course, the person who says, well, I don't take the theory literally, I just use it as a device to make calculational predictions, that person is not going to be moved by one more successful prediction. But if the alternative to quantum mechanics is, well, somehow, somewhere the theory must fail, because if it doesn't fail, we'll have people being alive and cats being alive and dead at the same time, I think that idea would have a blow against it in many worlds was true. Okay. Sorry, if quantum computers...
So, as for kind of the way we might revise thinking about our own lives in light of this, if we take it seriously. Now, one question is, of course, generally when we think of branches our own lives might have taken, different paths, we think of like choices we made. And that's the things we rack our minds over. What if I had done this? What if I had taken that job? Was this a mistake? Is there any reason? I mean, it would be great if this turned out to map on to quantum physics, but is there any reason to think that, from a philosopher's point of view, not necessarily just a physicist's point of view, but is there any reason to think that these branching points that you've described actually might correspond in at least some cases to choices that we make?
I think basically not, but it depends what your choice is. I mean, let's have an example. Suppose you're considering your career. Am I going to become a scientist, or am I going to go and work in the financial sector? So if you made the choice, if you sort of agonized and deliberated about this for a very long time, thought about the pros and cons, and finally came down on deciding that you should be a scientist, then that process at some macroscopic level is deterministic, probably. You did things for reasons and there are explanations for them. There's no particular reason to think there should be a branch there where you reach a different conclusion. On the other hand, if you basically can't decide, so you toss a coin or do some other sort of physically random process, then sure, in that circumstance, there'll be a branch in which things turn out differently. But insofar as our choices are made for reasons, then I don't think there's any particular reason to think there'd be branches where we made choices for different reasons.
Yeah, although, I mean, I guess the reason it's kind of appealing to think that the two might be connected is that free will is a mystery in its own right, right? On the one hand, it feels as if we're making choices, and in fact, if we took really seriously the idea that we aren't, that might lead us to a state of despair and nihilism and ennui. But on the other hand, the way we all actually intuitively think about how the world works when we examine it tends to be deterministic. And so we, in other words, you on the one hand, you intuitively feel you're exercising free will, but on the other hand, if you actually try to conceive of what free will would be like, you actually have a lot of trouble because we don't actually think the world works like that. So that's a deep, as you know, you're a philosopher, it's a deep problem. It's always nice when more than one problem can have the roots of a solution in the same thing, but you're dismissing that in this case.
I mean, I think it's nice, but it's often a bit too seductively nice. I mean, it's often very tempting to think we have this whole constellation of mysteries, let's all solve them in one go. Mm-hmm. I'm actually much more conservative about what the many worlds theory can do for us here. I mean, my feeling is that the main moves you can make in the free will debate don't play out that differently in a many worlds universe than in a deterministic universe. So I mean, for unoriginal reasons, I'm quite relaxed in my compatibilism. I don't think determinism and free will are deeply in conflict. But I think insofar as they are or they're not, I don't find myself inclined to think it changes much on many worlds. But I think the real clash is not so much between determinism and free will as between mechanism and free will. Can we reconcile ourselves between the idea that we make choices for reasons and we decide on them? Can we reconcile, and we could have decided differently, could we reconcile that with the fact that our brain is a mechanical process obeying microphysical laws that don't seem to be the sort of thing we can control, that are even the kind of thing where neuroscientists and psychologists seem to be able to say things about them, where people's upbringing affect all those things. Now that's maybe there's a problem there, or maybe there isn't. But if there's a problem between if there's a clash between my freedom of will and my brain being a deterministic mechanism, I don't think the clash goes away if my brain is a probabilistic mechanism, or even if my brain is a mechanism to do lots of branching. I mean, the branching would still happen because of microscopic quantum processes that I don't control.
Right. I'm not saying the clash goes away. I mean, first of all, I'd say, I think another way of saying what you're saying is that to the extent there's a clash, it's like, if you think of yourself as completely mechanistic, then in a sense you're thinking that you don't exist in the sense in which you've traditionally thought of yourself as existing, because you've thought of yourself as being this volitional actor that intervenes, and if you view yourself as completely mechanistic, there is no intervention.
Well, as I say, I don't actually buy there's a contradiction there, but that's how the argument would go.
That's how it would go. But see, when I'm asking if many worlds branch points might map onto what we think of as choices, I'm not saying that then the problem of determinism would go away. I'm just saying it would be interesting. but you think you have reasons for thinking it's not the case.
Well, I think there are good reasons to think it's not the case, but I'm kind of glad about that, because I think it'd be kind of horrifying. I mean, I take some really important, morally significant decision, and I think hard about it, and I decide, and I make the decision, and I decide I made the right choice. I think I made the right choice. The idea that any time I make a choice like that, there's another branch out there just as significant as my branch where I made a different decision. Well, now the whole idea I take a choice is a bit of a mockery. Really, it's just there are two versions of me. They made different choices.
Yeah. Well, I would think that the mechanistic view, leave aside quantum physics, makes the same kind of mockery of the idea of you like laboring over the right. It was all inevitable, relax. But so. Okay, so then what are the ways that this leads you to reflect on your own life in a different way? If it doesn't either add or detract drama from the big decisions you make, what kinds of reflections do you think it kind of validly leads to?
Sure. Well, I'll say something sort of general and then something a bit specific. I mean, the general observation is, I think, the main change it should bring on us is a sort of realization about our place in the universe that's kind of similar to the change in our take on our place in the universe that we had when we discovered that the suns were other stars. So the realization that the Earth wasn't the center of the cosmos, but we were going around the sun, and even more dramatically, the sun was itself just one part of a vastly larger cosmos. I mean, none of that directly changed anything about what mattered on Earth. It didn't change whether you enjoyed your job or your friendships were like, or whether whether you were ill or something. But it changed our broader sort of picture of our place in the world, and it changed our perspective on what humans were and what Earth was, in ways that have had very long-term philosophical, theological consequences. And I think the impact of the many worlds theory probably has similar implications than that. It's another demotion of our status in the universe, at least in terms of how much the universe is sort of built around us. In terms of a particular example, I mean, speaking personally, I think it makes vivid certain things about probability that we're traditionally very bad at thinking about. And again, I think this is something that you didn't need Everett for, but I think psychologically it makes it easier to realize. So I think we're very often in situations where we make sort of choices where things might work out or they might not, and that depends on sort of probabilities outside our control. And we're very often inclined to think that if the probabilities, if the thing worked out the way we wanted it to work out, then we made the right choice. And if it didn't work out the way we wanted it to work out, we made the wrong choice, even when the probabilities are quite skewed there. So, something like I have a 1-year-old. So suppose I do something. I'm reckless with my 1-year-old. I leave him in the car for while I go and get some shopping, leave the door open or something like that. Now, if I come back to the car and find he's fine, then there's a psychological temptation to think, okay, I got away with it. It's all right. And I think actually that's a very bad way of thinking about decision making. The point was you did something that was probably disastrous, or at least had a dangerously high probability of being disastrous. And the fact that in fact things worked out for you shouldn't reassure you. Now, in a many worlds theory, of course, you've got good reason to think that, because these aren't my choices, these are probabilities determined by physical factors. You've got reason to think that in those other branches, the circumstance turned out a bad way. And I think sort of thinking that those realities which have versions of you just as real as you yourself are, where the circumstance turned out badly, is quite a vivid way to remind yourself of the importance of having made the right decision there, even if, in fact...
Well, now, it's interesting that in this case, you are invoking a conscious choice as being at least relevant to this, right? Now, you're not saying that some quantum thing caused the choice.
No.
You're saying that, well, maybe like while you were in the supermarket, 2 versions of you were created, or 2 versions of your car were created, or whatever. And so it does still influence the way you think about choice.
Yeah, I mean, the difference is I'm thinking of choice here in terms of my own choice and not as a random process. And of course, there's all those free will problems we were raising are still there. But then separately from that, I'm thinking that the choice I make can play out different ways according to how various physical things in the world turn out. I mean, the most stylized version of this would just be gambling or something. So I could choose to gamble or choose not to gamble. And depending on what my choice is, I'll receive different rewards according to how different random things happen.
Mm-hmm. Well, what about if you make a decision and it turns out horribly? Should you take consolation in the idea that there's a version of you out there where things worked out fine? Yeah,
I think that's right. I think that's the flip side of the coin. I think one might legitimately be a little bit more stoical in these circumstances. You're on. This has never happened to me, obviously, but you're on the plane and some disaster has happened and it's going to crash. Perhaps you should be reassured by thinking, well, that was just my bad luck, and there are lots of versions of me just as real as this version for whom the accident isn't happening, and they'll go on to live lives that do the sorts of things I want to do with my life. Maybe one should be reassured by that. I suspect in the moment, maybe not. I don't know.
Right. Well, of course, if we were really capable of abiding by that kind of logic, then we would be able to greet all our grave misfortunes by reminding ourselves that there are billions of people on the planet who are having perfectly fine lives. Because, like the different version of me, they are not me, right?
No, that's right. I mean, so you might think, you might find that sort of adjustment psychologically easier when you know that this is somebody exactly like you, or you might not. I mean, I think these things, I think of these things as speculative at best. I mean, to be truthful, I wouldn't say that taking the many worlds theory seriously has radically changed my perspective on life outside thinking about quantum mechanics. I'm just guessing in ways that these ideas might if they're taken more seriously. And the metaphor is all over the place. I mean, you mentioned it yourself in Choice. Certainly the ability to think in these terms has infected the way people talk, even if they don't if they don't literally accept the theory as true.
Now David Lewis was a philosopher of physics who died, I think, more than 10 years ago. As it happens, he lived a few houses down from me, and at one point, a friend of mine, after he died, I forget how exactly this happened, he gave me a copy of a paper that Lewis had written that had not been published or maybe even finished within his lifetime, but he had sketched out implications of many worlds in a way that had a very grim kind of conclusion. Yes. Did this come to your attention, this argument?
Yeah, the paper was published in Lewis's sort of posthumous collection of his work. And it's actually an argument that had been around. I don't think Lewis knew this. It had been around in sort of folk conversations in the physics community for quite a long time before it was published. But Lewis's article brought it to the attention of the philosophy community.
And how does it go? Is it possible? I've forgotten totally what it was.
Well, the way it works is supposed to be something like this. So suppose that something is about to happen that's going to kill me very suddenly, or maybe not. So I'm stuck in Schrodinger's cat's box. So if the atom decays, I quickly die, and if the atom doesn't decay, I live. So the idea of these examples, they get called quantum Russian roulette sometimes. The idea is supposed to be that what I ought to expect to happen normally, if you just think of quantum mechanics as a random theory, is that, well, maybe I'll die or maybe I won't, who knows. In the many worlds theory, of course, what you should expect is that there will be some branches in which I die and some branches in which I don't die. And what Lewis has argued, and what many people in physics have argued, is that being the case, what you should expect is to be one of the people in the continuing branch, because you can't expect to die. You can't expect not to have expectations. That's how the argument goes. So it's supposed to be the case. I should say up front, I don't really buy this argument, but it's supposed to be the case that what you should expect in any situation where normally we'd say you have some chance of survival is certain survival, because there'll always be some version of you that survives. And Lewis's argument, and as you say, it's pretty grim, is that in many situations, in pretty much any situation in which we might die, there are always going to be some ways I could have survived, but very often they'll involve me surviving in a very badly injured state or something like that. Mm-hmm. So what I should expect is gradually I get sort of more and more decrepit and injured and so forth, but I never actually die.
But you never actually die. Well, a version of you never actually dies.
That's right. I mean, right.
I see. So if you kind of identify, suppose you want to identify with all the versions of you, and like you might say right now, only 5% of the versions of me are in a dire way. As time goes by, it becomes closer to 100% of the versions of you that are in bad shape.
That's right. Yeah. Uh-huh. I mean, this isn't an argument I'm very persuaded by. I mean, I think it comes down to some quite subtle questions about how you talk about survival and death. I mean, I'd be inclined to say the right thing to say is that most of the versions of you are dead, and to have a slightly more third personal take on it than that. But
I mean, another kind of objection to his argument, it seems to me, is like, why would you expect that the world we see, where life expectancy is so on, such and such, and being old tends to be like this, why would you expect that it's anything other than typical? Why, right? Why would you? I would think we see the likely probabilities in this world, and I don't understand why this wouldn't be typical of all worlds, but maybe.
Well, it would be, but the argument's supposed to be that we're not interested in what's typical of all worlds. We're interested in what's typical of the subset of worlds in which I have conscious experiences.
Yeah, I see.
Because on this argument, that's what
I see. So it's like, I get it. It's like right now I look out and I see somebody and, they're like 90 and, everything has gone wrong. It just couldn't be worse. And, but almost nobody's winds up in a situation quite that bad, so you don't have to worry. And Lewis would say, no, actually, there's a chance that there will be a version of you somewhere that will be in that situation.
Yeah, I mean, the argument's supposed to be, look, in the distant future, in 100 years' time, let's say, there will still be some branches in which you're alive, but they're nearly all branches in which you're sort of clinging to life and in terrible pain and so on. Now, I mean, look, Dave, I've given a sort of philosopher's response that I think this is the wrong way to think about personal identity and expectation. David Deutsch gives a much more straightforward answer, which is something like, well, look, in 200 years' time, let's say, in a vastly higher fraction of those branches, there will be medical advances of various kinds, according to which you're alive and well and perfectly happy. Even if that's not very likely to happen in 200 years, it's vastly more likely than this sort of tiny series of incredibly unlikely events that keeps you clinging to life. And I think that's a fair response as well.
Right. One version of you will live to a point where life expectancy is growing by more than 1 year per year, and then you're safe forever.
And then you're fine. Yeah, I guess.
The identity question. I mean, that's the other thing is like, and I know it doesn't make sense to think this way, but it's hard to escape it, which is like, I mean, you look back and there's this continuity of identity. And so you want to ask this question like, well, at the last branching point, what determined that I would take this path? But of course, that doesn't make sense. You just broke up into two.
Exactly right. Yes, and you both. I mean, you have a unique predecessor, but not unique successors. Yeah. So I can remember my part. I have a unique past. I can remember the previous David perfectly well. But yeah, there's no fact of the matter as to which is which. There's just a branching. Now, the language we might naturally, the language we use to describe that, a language of uncertainty from a purely subjective point of view, might carry on being a sensible way of using language. Or we might think that the meaning of our word uncertainty changes a little bit once we learn about many worlds. But yeah, there's certainly one can't expect to look for some additional physical fact that determines which one you are.
Okay.
But it's almost, this is an analogy. It's a bit analogous to asking, why am I me and not you? I mean, the reality is there's a person who's you and there's a person who's me, and each of these people has the experiences they have. To ask of each of those people, why are they that person and not another person who already exists? It's a very tempting question. It's the kind of thing kids getting interested in philosophy think, but ultimately it's not really a coherent question unless you accept a sort of disembodied soul that could be in one place or another.
Now, I've seen references to the quantum suicide thought experiment, and I gather that you don't encourage people talking about this a lot because, in principle, there could be somebody out there crazy enough to act on it. Or are you?
Yeah, I mean, I don't want to overstate that, but I mean, I think there's nothing. Okay, so I happen to think the argument's not a very good argument, but there's nothing wrong with serious discussions of arguments that I don't think are good. The context of that remark of mine is just that I think sometimes the argument gets thrown around as just like a fun thing to talk about the many worlds theory, and I think it's a bit dangerous to treat it that way as a casual thing. It doesn't mean I want to suppress conversations about the topic.
Does it mean you'd rather not describe it now, or?
Oh no, I'm happy to.
Okay, what is the quantum suicide?
Well, it's kind of it's pretty much the framework we discussed with Lewis actually. So again, the idea of the experiment is something like I set up some random process that might lead to me being rewarded, or it might lead to me dying. And the classic example is I play Russian roulette for high stakes.
I see. And
again, the idea is in the none-Everett setup, then what I should do is not play because probably I'll die. And the small chance of getting some money doesn't outweigh the probability of dying. In the Everett scenario, I will definitely continue in the sense that there will definitely be a continuing version of me, and they'll have the money. Therefore, so goes the argument, I ought rationally to play Russian roulette.
Well, it depends on how you're thinking of your future identity. I mean, there will be fewer of you than there might have been, and one might logically identify equally with all future versions of yourself.
Yes, indeed, including the dead ones.
Yeah. So I will not be doing that experiment.
Yeah, I think well, very wise. I think that's right. I think the argument partly hinges on a mistaken view of how to think about personal identity in these examples. I think, to be honest, it also rests on a philosophically quite naive view about why we care about dying. I mean, typically, if one's concerned about death, one's concerned about one's goals that are no longer fulfilled, one's plans that don't happen. one's removal from the sort of network of friends and relations and family and projects that matter to us. And of course, you're being removed just as much in all these cases.
Okay. Now, let's talk about, before we go, one more weird quantum mechanical phenomenon, which is entanglement, which I gather, is that related? Is entanglement in some ways related to this? I mean, it's weird enough to be worth talking about.
So entanglement is very centrally related to this. So entanglement is a phenomenon where you've got two systems interacting, and it stops being possible to talk about the states of the two systems separately. Or stops being straightforward to talk about the states separately.
Okay,
So
and the more exotic description, right, is that, like, you've got these two particles, their properties, there's a certain property, say spin, that tends to be, related. You could think, it tends to be complementary, I guess. So you could think of, like, the deal is with these two particles, which used to be real close, one is going to be heads and one is going to be tails. At all times. You don't know which one. They fly apart, and you measure one, and that measurement, by, to speak in the language you reject of a wave collapsing, but let's just say the measurement forces it to be either heads or tails, and that in turn determines instantaneously that the other one will be the opposite. So you've got a case of, in a certain sense, influence moving instantaneously. That's not the same as information moving instantaneously, because you can't use this for communication. But still, it's weird. It's so weird that Einstein thought it couldn't happen. And that's one exotic way of describing entanglement, right? Their fortunes are entangled forever, but that's not just in the sense that because they were correlated at birth, they will remain correlated forever. That's true, but it is thought that it's thought that neither one had this definite property until you measured it, and that's the sense in which you're influencing the other one across all this distance.
Yeah, that's pretty much right. I mean, this goes to the heart of the puzzles of quantum mechanics we started with. So remember, we were talking about the fact that the quantum state, the quantum system, at the microscopic level, you can't think of it in probability terms, but then later it seems you have to. So the temptation for entanglement is just to say very mundanely, well, there was a 50% chance that particle 1 had spin up and particle 2 had spin down. There was a 50% chance the opposite was true, and we just found out which one. And the reason you can't do that is because there are microscopic level experiments you can do on the quantum system that rule out that probability interpretation. So once you realize that, then really entanglement is just what you get when you consider this property that quantum systems can do two things at once, and then you think about more than one quantum system. So we had the electron that could be here and there at the same time. So now suppose I've got two electrons, and the joint state of the two electrons is they're both on the left and they're both on the right at the same time. And now if you ask, where's the first electron? You can't say it's on the left, you can't say it's on the right, you can't even say exactly that it's left and right at the same time. All you can say is what it's doing relative to what the other electron's doing.
Okay.
Or you can give a joint description of what both electrons are doing, and that's entanglement. And it's central to many worlds, because you remember when I was talking earlier about how I end up doing two things at once and you end up doing two things at once, but they're all correlated. Entanglement is what makes that happen. So you can't talk separately about my state and in the quantum many world situation, you can't talk separately about my state and your state and the cat state. All you can talk about is our joint state. So the joint state of you and me and the cat is cat dead, I see cat dead, you hear me say cat dead, plus cat alive, I see cat alive, you hear me say cat alive at the same time. And it's because of that that the language of worlds makes sense. If all the objects in the world were independently doing two things at once, you'd just have a sort of chaotic soup. You wouldn't have many worlds.
So you're saying entanglement kind of imposes coherence on the different worlds, or?
Yeah, I mean, it's ironic to use that word because decoherence is exactly the word we use to describe it. But yeah, entanglement is what makes the world structure happen.
I mean, otherwise it would be nonsensical if, I mean, it's almost the definition of what a single world is, that there is coherence in my sense of the term. And you're saying that is due to entanglement?
That's exactly right, yeah.
So entanglement is the glue that at any given point is holding all this together?
That's right. So, I mean, Schrödinger famously said, I think this is Schrödinger, that he used to think what was mysterious about quantum mechanics was superposition, which is the here and there at the same time thing. And eventually he decided, no, entanglement is the real mystery of quantum mechanics.
And it is
really important feature of quantum mechanics, I should say.
And it is weird. I mean, again, Einstein, he thought it was like the reductio ad absurdum because he didn't buy quantum mechanics in the form that it came to assume. And he said, look, if quantum mechanics were true, you'd have this entanglement thing, and that couldn't be the case. So quantum mechanics can't be true, right?
Yeah, but notice the thing he's really bothered about, the idea that somehow there's an influence that travels faster than light and so violates his theory of relativity, that only happens because we collapse the wave function. That doesn't happen in the many worlds theory. So there's no faster than light effect in many worlds. You said at the beginning that's one of the reasons the physicists are taking it more and more seriously. One of the reasons physicists like the many worlds theory so much is because it's very straightforwardly compatible with relativity.
Oh, I see. So if you he was accepting like the Copenhagen interpretation as typical of quantum physics, and under that, then entanglement would violate
something
relativity?
Like that. Yeah, that's basically what it's doing. Yeah.
And just quickly, Copenhagen interpretation is that a subset of the second interpretation I described earlier? That's a version of the wave function collapsing?
Well, it gets used to mean lots of things. I mean, as modern physicists use the term Copenhagen interpretation, it very often means what you described. A measurement process collapses the wave function. Niels Bohr and Werner Heisenberg, who were the sort of co-founders of the Copenhagen interpretation, they meant something quite a lot more subtle, something more like what I was calling a change the philosophy approach. Think about understanding a theory in a different way. And what they meant is contentious, and they didn't seem to mean exactly the same thing. And Bohr in particular is a famously obscure writer, so it's not a straightforward thing to say exactly what they meant. But I suppose they were both committed to the idea that somehow you can't treat a physical theory as just describing an objective world in a way that's independent of the role of the observer in that world. I mean, so Chris Fuchs, who's an advocate of sort of modern versions of Copenhagen, sometimes talks about, I think this is his term, a sort of participatory realism. So he wants to say he's taking a realist way of thinking about quantum mechanics. He doesn't like the sort of instrumentalist, operationalist gloss, but he'd want to say this is a picture of realism which has an irreducible role for the agent or the observer. Whereas on the normal way we think about most scientific theories, and especially the way the Everett interpretation works, then a scientific theory is just a sort of third-party objective story of what's going on, and it has observers in them because observers are physical systems, but observers are not a central part of understanding the theory.
Okay. So, when people take entanglement in a kind of new age way, or they say, well, so we're all interrelated and maybe, psychic phenomena can happen across space, or whatever they want to say, is it the case that many worlds actually makes those ideas less plausible in a sense?
I'm not sure they could be made any less plausible.
But you kind of know what I mean, right? I mean,
yeah, in a sense that's right. So on a collapse story where measurement collapses the wave functions, on your second story, then something is happening that is faster than light. In some sense, and that something, as you rightly say, is not something we can use to signal or send information. But you can see how somebody might think, well, look, if your theory already says there are mysterious influences that travel faster than light without any intervening medium, then it's not so much of a bigger step to say, well, maybe we can use those influences to do weird psychic stuff. I mean, I should be really clear, I don't endorse that for a moment, but you can see how people might be tempted by that suspicion. Even the starting point of the temptation is not available in many worlds theory. And look, this is a general feature about many worlds. I mean, you started this by saying it's weird, and of course it's incredibly weird, but in another sense it's really conservative. And again, that's quite linked to why physicists like it. It's really just a very literal-minded reading of the mathematics we already have. And so its weirdnesses are sort of anti-common sense weirdnesses, but they're not sort of weirdnesses internal to physics.
Well, so, and also it removes certain other forms of weirdness, right?
Yeah. Yeah, I mean, from a physicist's point of view, violating common sense, or if you've got a choice between violating common sense or violating the theory of relativity, you're going to violate common sense anytime.
So the deal with quantum physics is just choose your weirdness, but it's going to be very weird. There's no non-weird interpretation of quantum physics.
There's no non-weird interpretation, but I want to push back against the sort of choose your poison framework. I mean, the alternatives to something like Everett are either changed the equations of quantum mechanics, and it's the most successful scientific theory ever, or it's dropped the idea that what you want to do with a physical theory is to tell an objective story about the world. So, I mean, you could say those are different varieties of weirdness, but I think one thing is not like another here. And you generally get, there's reasonably wide consensus, at least in philosophy of physics, that if the many worlds theory can be made sense of, it's the sensible theory to adopt. Now, most philosophers of physics don't accept the many worlds theory, but mostly they don't do so because they think the many worlds theory doesn't make sense for one reason or another. They mostly accept the conditional that if it could be made sense of, it would be the best way to think about things.
But the number of them who support it has grown in recent years. Is that right?
What, in philosophy of physics? Yeah, I'd say so.
And I think I read somewhere, maybe you said it, that actually many physicists accept it. Now, in my experience, there's actually a certain number of physicists who just don't even ask themselves the question of how the math, what the implications of the math are for the real world.
Yeah.
But you're saying of the physicists who think philosophically, is many worlds the favored interpretation?
It sort of depends in your physics community. So if you look at people who do particle physics or cosmology or string theory, of those people, of the ones who think about it, which as you say is only a minority, but of the ones who think about it, I say Everett is the strong preferred choice in that group. If you look at people who work in sort of quantum information, quantum computers, then probably at least as many of them like some modern version of Copenhagen, where the sort of you've heard sort of slogans like physics is information, so people are drawn to that kind of story. It's kind of, I mean, look at it this way. I was talking earlier about you get many worlds if you do two things: leave the physics alone and leave the philosophy alone. So physicists are very keen on leaving the physics alone and quite relaxed about changing the philosophy. Philosophers are quite relaxed about changing the physics and leaving the philosophy alone.
Okay.
My kind of suspicion is that physicists recognize how difficult it is to change the physics and don't recognize how difficult it is to change the philosophy, and philosophers are vice versa. But I'll freely admit that I have a vested interest in thinking that way.
Right, but you are intent on not changing the physics. You are a philosopher who is intent on not changing the physics.
I prefer not to change the physics or the philosophy. I would like to be quite conservative with everything except common sense.
Okay, well, you can't have everything. Okay, well, thank you very much, David. Now, I mentioned your books, in particular, the Emergent Multiverse with Oxford University Press. Are there things you've written, papers or whatever, that are particularly easy introductions to, or particularly accessible introductions for lay people?
I haven't ever really done a long form, purely lay people introduction. I mean, I've been sort of pleasantly surprised by how many bits of things I've written people have been able to understand and make sense of. But there's nothing I've written that makes a systematic attempt to avoid the equations. I mean, I think my advice is the same as Roger Penrose gave here, which is that you can just skip or skim the mathematics.
Right.
But that sometimes
and you know, and your book, The Emergent Multiverse, I think, you know, you could. I know you started with a. We didn't have time to get into this, but a kind of interesting analogy between this whole question, the theoretical, the interpretation of quantum physics, and questions of like paleontology, like you know, if you making sense of the fossil record with and without thinking of actual dinosaurs as having evolved, and so on. So, I mean, people could start reading it and get it, I think. So,
yeah, I mean, I didn't write the Emergent Multiverse for a lay audience, but I've been pleasantly surprised how many lay people have told me it's accessible. I mean, there are bits where there'll be tens of pages at a time of mathematics that just have to be skipped, but the bulk of it, I think, is fairly accessible.
Okay, so we'll steer
sort of on my project list to do something more lay accessible, but.
Well, maybe somewhere one of you is already doing that.
Right, yes. Somebody's thought about their strategy rather better than me.
You can take consolation in that. Okay, well, thank you so much for taking the time. I know you have to go teach, so enjoy that. And we will see you around.
Yeah, thanks. Enjoy it.
Bye-bye.